Hi guys, so I'm going to go through this as quickly as possible. I usually end up making videos that are way too long, so I'm going to try and keep this quite short. So I'm not going to go too much into the conceptual understanding of how this works because we did this in chapter 6 and 7. I'll let you read over this part of the note sheet, but suffice it to say that we said when we add or subtract sampling distributions, the shape of the sum or difference distribution remains the same. So adding or subtracting sampling distributions didn't change the shape. And also adding and subtracting random variables, the mean of the random variable worked this way, right? So the mean of the difference of two random variables was the difference of the two means, and that gave us a simple way of calculating the mean of the resulting distribution. So I'll let you think about this. It's quite deep conceptually, but I'll let you think about this and just read that over. And then you'll see kind of where our calculations come from that we're going to use for this section. Okay? So let's just talk about what the sampling distribution of a difference in proportions looks like. It says choose an SRS of size N1 from population 1 with proportion of successes P1 and an independent SRS of size N2 from population 2 with proportion of successes P2, and then this is what would happen. Okay, so as long as the first sampling distribution for the first population meets the large counts condition and the second sampling distribution for the second population meets the large counts condition, then the difference distribution or the sampling distribution of the difference in proportions will also be approximately normal because the shape doesn't change. All right, and then the center, the mean of the sampling distribution of the difference of two sample proportions is equal to the difference in the population parameter proportions, okay? And standard deviation would be this. And I think that's what we saw in the previous example there, okay, when we did a review of chapter 6 and 7. So, remember, standard deviation can only be calculated when the 10% condition is met. So here's an example that walks you through checking conditions. So it says, suppose there are two large high schools, each with more than 2,000 students in a certain town. At school 1, 70% of students did their homework last night. Only 50% of the students at school 2 did their homework last night. Counselor at school 1 takes an SRS of 100 students and records the proportion P hat 1 that did their homework. School 2's counselor takes an SRS of 200 students and records the proportion P hat 2 that did their homework. Schools 1's counselor and School 2 counselors meet to discuss the results of their homework surveys. Oh, okay. After the meeting, they both report that to their principals that the difference in the sample proportions was 0.1. So describe the shape, center, and spread of the sampling distribution. So let's talk about shape. So shape. So now we have to do some calculations based on all of this right here. Okay, so we have to check the first distribution for normality. So just remember something. This number here and this number here, those are actually the truth. So we were given P here, and let's call this P1, and we were given P2 here. These two numbers are actually the truth. And these difference in proportions here, sample proportions, comes from the samples. Okay, so the shape, we can check the shape of the first distribution by doing N1 P1 greater or equals to 10 and N1 1 minus P1 greater or equals to 10. And we just do the calculation. So my sample size for the first school was 100. So this is my N1, this is my N2. So we're just doing 100 times 0.7, and that's 70, and that's greater or equals to 10. And then we do 100 times 0.3, and that's 30, and that's greater or equals to 10. All right? So what we have is that the large count condition is met for the first sampling distribution, and then for the second one we have N2 P2 greater or equals to 10, and N2 1 minus P2 greater or equals to 10. All right, and so if we do this calculation, we get 200 times 0.5 greater or equals to 10, and this is actually just 100. That's definitely true. And this one would give us the same. I know this is tedious, but just remember you have to actually write this stuff out. Okay, and so we can say that the distribution of the sampling distribution of p hat 1 minus p hat 2 will also be normal. So since the large counts condition was met for both sampling distributions, okay, the shape of the sampling distribution of p hat 1 minus p hat 2 is also approximately, that's a capital N, normal. Okay, and then center, well, we said that earlier if you looked at the previous page. So we know that the mean of this is equals to the mean of the difference in the means, and that's equals to P1 minus P2, and we have that, which is 0.7 minus 0.5, which is 0.2. So that would be the center, and then the standard deviation, which we're calling spread. The spread will be measured by the standard deviation of the difference, and I think we have, this is this formula right here. Okay, so that would just be the square root of, and we should probably get used to just writing this a few times so we don't forget it, like this, and then just fill in the numbers. Okay, so fill in the numbers, so you get 0.7 times 0.3 over 100 plus 0.5 times 0.5 over 200. All right, and if you work that out, I think you get 0.058. Right? So that's just walking you through checking the shape, center, and spread of a sampling distribution of a difference in sample proportions. Okay, so I mean, I didn't really motivate this, but why would I want to do something like this? To see if I can actually make the claim that one school has a higher percentage of students who do their homework than another. Or let's say one candidate has a higher proportion of people who want to vote for him in a city than another candidate. And so we would compare proportions. So the reason we're subtracting them is to compare which one is bigger. Okay, can I actually see a definitive answer for one being bigger than the other? Or for there being a difference at all. Maybe there's no difference. Okay, so that's why I want to even engage in something like comparing two proportions, because we frequently generate two proportions and we want to compare them somehow. Comparison for us would be subtraction to see if the difference is 0, then there's no difference. And if the difference is not 0, then we know something is going on, and we can determine in which direction. Okay? So, all right, so now you know about the shape of the sampling distribution, so you should be satisfied that we can find the center, we can find standard deviation, and we know the shape. So if we know the shape is approximately normal, we can do probability calculations. And we can also do inference procedures based on this. So, of course, we did confidence interval for a single proportion in the previous chapter. Well, actually, that was chapter 8. So in this chapter, we're doing a confidence interval for the difference. Okay, so what are plausible values for a difference in two proportions? That's the question. And here are the conditions. Surprise, surprise. Random. So this is quite tricky, though. I think you need to get used to this. The data come from two independent random samples or from two groups in a randomized experiment. So the experiment thing we'll hit on, I think, a little bit later. That gets quite tricky, but two independent random samples is actually very specific. So I'll explain that to you by doing this. Okay, so you have to do this. You actually have to say that if this is my sample 1, okay, so if this is my sample 1 and this is my sample 2, we want to say that these samples themselves are independent, okay, but also we have to be able to say that the individuals and their responses inside the group are independent of each other, okay, independent. So that's quite tricky. So we will have to think about that. So you want to have independence within the samples here. Okay, you want to have this kind of a claim, which actually we will test this with the 10% condition. Okay, we will check this with the 10% condition. But this is not so simple. You have to make some kind of a claim that it's reasonable to assume that the samples are independent of each other. Okay, so we'll talk about that. And then 10% condition, okay, so we said that's what would satisfy that individuals in the sample are independent of each other. And then large counts. Okay, large counts. So again, we just did this. In this case, for a confidence interval, we will use n1 p hat 1, n1 1 minus p hat 1, and so on, because we don't actually ever know p and p1 and p2 like we did over here. We were given the truth. We don't actually know the truth. So for a confidence interval, these are the conditions we'll check. Okay, not much different, except we're now adding a second sample into the mix because there's two proportions, so two samples. Okay, and two populations. All right.